Namaskar and welcome back to the course on statistical mechanics of phases and phase transitions. We have explored Ginzburg-Landau theory within the saddle point approximation to see whether we can extract critical exponents that match experiments. Unfortunately, that did not work out, yet we found the following very interesting results. So, in the ON vector model of Ginzburg-Landau theory, we noticed that long wavelength modes contribute to a divergence of specific heat when d is less than 4. When t is less than 0, namely you are in the broken symmetry phase, we observed that there are two types of fluctuations. Ones that are longitudinal, in the sense that there are fluctuations in the same direction as the order parameter that has developed, and the others are transverse. And we noticed that the transverse modes do not contribute to any thermodynamic quantities, temperature dependent thermodynamic, T dependent thermodynamic quantities. We then noticed that the only thing that these fluctuations do is they will change the critical exponent of the specific heat in dimensions less than 4 to 4 minus d, and you will obtain an amplitude ratio for the specific heat which has some information about the symmetry. Okay. The other critical exponents are unchanged and they certainly do not depend on d and n and all that. And if we were to take some consolation of the work we did, then we will see that Landau theory becomes exact in the sense that the jump in the specific heat is preserved. It may change to a new value, but it does not change the exponent of the specific heat, etc., when dimension is greater than 4. So, this is the main result of what we found. So, you might think that okay, we have not gained anything by doing Landau theory, but I will in this lecture try to show you that is not the case. Actually, there is a lot of things, it has not worked, but it teaches us in some sense we will find out why it is not working. Right. So, that is what this lecture is about. And so, what I want to do is, I want to motivate some of these ideas by pointing out that you should try to work closely with experiments, in the sense that taking known experiments, so that you can keep testing theory and experiment, and you can sort of understand what are the limits of your theory and how you should think about your theory when looking at real systems and so on. So, you will see that today's lecture has a lot of, if you wish, physics content, right. And what we will do next is we will look at the fluctuations near the saddle point, and we will understand more about these fluctuations that we have introduced in the last lecture. Okay, so let us kick off today's lecture with a puzzle, right. It is always good to have some experimental puzzle. So, we have seen in previous lectures that both superconductors and superfluids, superconductors are electrons that become superconductors, and superfluids are like bosons like helium-4 and things like that, which undergo superfluid transition. And we know that they are both described by a U1 symmetry, or which is equivalent in our language to O2, right. So, here is some data for specific heat. Remember, there is no theory here, it is all measured data, and what is shown here on the left hand side is the specific heat of aluminum, which becomes superconductor, something like some 1.2 Kelvin or something, right. And this is the specific heat of superfluid helium as it undergoes this lambda transition. Okay. So, let me walk you through what is the result here. So, Cs stands for the superconducting specific heat, okay, and Cn stands for the normal specific heat. So, how should you read this graph? You should read this graph as if the superconducting specific heat is going up, and this is Tc at which superconducting transition takes place. At that Tc, it jumps down and then it follows this. So, you see exactly a jump in the specific heat, just as predicted by Landau theory, in 3 spatial dimensions, right. And next is, this is also a transition that is undergoing a U1 symmetry breaking transition, if you wish, O2 symmetry breaking transition, but here you see a very prominent divergence of the specific heat and not a jump. So Landau theory predicts that there should be a divergence of specific heat in d equal to 3. It's 4, alpha is 4 minus d by 2. So it should be half. Okay, so this looks very encouraging because this looks like what we find in lambda theory. So the main point is superconductors show jump discontinuity of the specific heat at Tc. The superfluid transition has a very clear divergence. In fact, the name of this transition itself comes from this shape of the specific heat, that is why it is called the lambda transition. So the natural question to ask is, why does the superconductor behave so close to Landau theory predictions and the other does not, and it seems to have some critical features, right? It has some divergence specific heat and so on. So why is this difference showing up? So you may think that, okay, we have to do some more detailed theory for this. So the answer turns out to be no. You can understand this by our Landau-Ginzburg theory within the saddle point approximation, and that is what I am going to take you through here. Okay. So naturally we have to understand what Landau theory is, right? We wrote many things down, but we have to understand what it actually means. So the Landau result for thermodynamics, I am going back to the Landau theory which we did many lectures back now. So f of t goes as t square by u is the parameter in the Ginzburg-Landau theory for t greater than 0 and t less than 0, and specifically it does this. So let us first think about some dimensional considerations. So if you think of the free energy density we wrote down, the way we have constructed the theory, the free energy density will be simply a density, as we have emphasized throughout. Density has dimensions of 1 by length to the power minus d. So a warning on notation, when it is, see, suppose it is some kind of italicized L, that is the system size, the edge of a cube or something. When I am writing things which are not italicized, which are in the same font as the background text, like L to the minus d, that L stands for the length dimension, right? When we remember when we were in high school, we were taught units and dimensions. So this is length dimension. So this free energy density has dimensions of length to the power minus d. It's actually a density, number density, some 1 by volume kind of object. Okay, so that is what this is. So what would that mean for the dimension of u? So that will immediately, okay, since t is dimensionless by construction, specific heat also has dimensions of L to the minus d, right? Because I am just taking derivative with respect to dimensionless parameters. So this will tell us that the dimension of u is L power d. So in the way we have set up the Landau theory, simply from considerations of dimensions, you will see that this parameter u that we introduced has to have dimensions of length to the power d, right? So this means we can argue what this dimension of u is. Remember, Landau theory and mean field theory are the same thing. Landau theory is a way of phenomenologically doing mean field theory. Now when we did mean field theory, what did we do? We went to a particular site and we said that, okay, this site is seeing some average magnetic field from other sites and so on, and we studied, the problem effectively becomes a problem of isolated spins, each of which is seeing an effective magnetic field coming from other spins. So in a sense that the free energy density of the mean field theory will measure how many degrees of freedom are there per unit volume, if you wish. In other words, you can interpret this u as some length, microscopic length scale which contains some unit or some number of microscopic degrees of freedom in the ultraviolet. So it could be, you can think of it like the number of degrees of freedom per site of the microscopic model. So this is a physical interpretation of this based on the connection between mean field theory and Landau theory. So I can posit that u is some a naught to the power d, where A naught is some microscopic length scale. So that volume A naught to the D, if you wish, contains 1 degree of freedom, 1 microscopic degree of freedom. So that is a way of interpreting this Landau result, which is a very physically appealing way of thinking about specific heat itself, right. Okay, so this is the idea. Okay, so we have now interpreted the Landau specific heat as 1 by 2u as 1 by some microscopic volume. Okay, very good. So this is one side of the story. Now let us look at Landau-Ginzburg theory and try to figure out what can dimensional analysis teach us there. Okay, so this is the Landau-Ginzburg action written with no further approximation other than whatever is put in physically here. So this is the action functional, and I am going to exponentiate this action functional. So I cannot exponentiate anything with dimensions, I can only exponentiate numbers. So S of phi must be dimensionless, has to be dimensionless. Now this is an integral over a volume, right, and therefore there is an integration measure. So this has dimensions of L to the power D, and therefore this whole object here has to have dimensions of L to the power minus D. In particular, if I look at this term, I know that T by explicit construction has no dimensions. So what this means is that the field phi has to have dimensions L to the minus D by 2, so that when I integrate this over this, I will get L to the minus, when I square it I will get L to the minus D, and cancels the L to the D that comes from the integration measure. So I have now extracted the dimension of phi. Once I extract the dimension of phi, I can find out what is the dimension of y, the parameter y. What would that be? You can see that the parameter of y, by a simple calculation, its dimensions will be L square. And what will be the dimension of u? Dimension of u by this dimensional analysis will be L to the D, which is beautifully consistent with what we found from our argument on Landau theory. So this is all beautifully consistent. Okay. So now we already know that this is the result we obtained from Landau theory, and it has L to the D dimension. So I have this y which now depends on L square. So I have to introduce another length scale in the problem, and this is what I am going to do. I am going to say y is some length scale lambda naught square, and lambda naught is some length scale coming from microscopic considerations, what not. It is not determined by symmetry, it is something that the theory has to give us. So you have to put in, if you do not know how to do it from microscopics, right. Yet we know that there has to be a length scale lambda naught, and this is the scale that determines the stiffness. So in some sense this is the scale over which these microscopic degrees of freedom conspire, and they form some object which has some stiffness, right. Okay. So what we have done is something quite remarkable. By very simple dimensional analysis, we are able to find that the theory has this length scale lambda naught associated with the stiffness, and a scale A naught which sort of is the volume, A naught to the D will be the volume occupied by a degree of freedom or something like this. Okay, so this is what we have. Alright, now you may wonder, okay, this guy had started talking about experiments on superfluids and superconductors. What has all this dimensional analysis to do with that? I will say everything, and that is what I am going to show you in the next slide. Okay. So what I am now going to do is I am going to compare the specific heat coming from the fluctuation contribution, that is the Landau-Ginzburg-Gauss, and Landau, and the specific heat coming from this. So if you take the specific heat expression coming from the saddle point Gaussian approximation for t less than 0, so you are in the broken symmetry phase, you have two pieces. There is this 1 by 2u piece which contributes to the Landau jump discontinuity, and then there is the fluctuation piece which goes like this. Okay? Alright. So the natural question to ask now is, how close should be should I be to t equal to 0, which is where the critical point is, so that the fluctuation term starts to dominate this Landau jump discontinuity. This is what I would like to find out. So, how close should one be close to the transition so that the Gaussian fluctuation term can actually dominate the Landau term? Okay. So, this regime of T is denoted by Tg after Ginzburg, who came up with these arguments, and you can show simply by looking at this, take this to the left side, take magnitudes on both sides. So, you will see that this Tg to the 4 minus d by 2 goes as y to the d by 2 by u, which based on our discussions of the previous slide goes as lambda naught by a naught to the power d, which tells us that the Ginzburg window, right, the Ginzburg window of Tg for us to see the fluctuations dominating the Landau piece will go as 1 by lambda naught by a naught to the power 2d by 4 minus d. Okay. So, in doing this calculation I am making estimates. So, you see there are a whole bunch of constants here, I am not accounting for them because they are not critical for me to get orders of magnitudes. Maybe within 1 or 2 orders of magnitude they will not affect my results. So, I am just not going to worry about keeping those kind of details, right. So, this Ginzburg window estimate for us is the following. So, if t, little t, the distance to the transition, if it is less than this Ginzburg window, then the fluctuation term is bigger than the Landau jump discontinuity. So, the question is, how big is this Ginzburg window, right? Okay. So, if you take d equal to 3, then you will see that the fluctuations dominated regime is such that when t less than Tg is less than 1 by this thing. So, if you look at helium 4, you will see, and you can do the experimental estimates of this. So, lambda naught by a naught will turn out to be 2. So, this will turn out to be something like, say, let us say 2 to the d is 6, and you see 4 minus d is 1. So, 2d is 6, so it will be 1 by 2 power 6, which will be roughly of the order of 1 by 100 or so. So, Tg is of the order of something like 0.01 or 0.001 depending on what kind of estimates you are using, 2, 3 or 4 or something like that, you will get the Tg's of this kind. So, this looks pretty consistent with experiments that if you go to like temperatures like 0.2 or 0.02 of 2 Kelvin, 2.17 Kelvin or something, then you see this divergence. But here is the main story. In superconductors, you will see that this lambda naught by a naught is 1000, right. So, it is called the coherence length, and the coherence length by a naught is like 1000. So, what that does is it tells you that Tg is 10 to the minus 18. So, that means that to see the fluctuation dominated specific heat, you have to be within 10 to the minus 18 of the transition point, which is impossible to observe. And this is why you see that within the experiment you will only see the Landau part, because the fluctuation part, for it to come to play, you have to be very close to the critical point, right. I mean, it's I do not even know whether we can even think about think about what does it mean. It's a 1 Kelvin 10 to the minus 18 Kelvin, right. So, you cannot even control temperature to that kind of precision. So, what this means is that the critical region is basically non-existent in these traditional superconductors, and this is why, despite the fact that Landau theory is predicting divergent specific heat, you do not see the divergent specific heat in the superconductor experiments, whereas you do see some kind of divergent behavior, that is these fluctuation effects coming up and playing havoc in the case of helium 4. So, yes, so you see, even though we are not able to pull off the critical experiment story, we are able to understand some qualitative aspects of experiments from the study of Ginzburg-Landau theory even within the Gaussian fluctuation approximation. So, this is actually, as you can see, is very useful, And as we will proceed in this lecture, you will see that this has Landau-Ginzburg theory has a lot more to teach us. Okay, so we have now made some contact with experiments. We know that there are some qualitative aspects of Landau theory, Landau-Ginzburg theory within the saddle point approximation, which is good, help us explain variety of things. Let us proceed and let us explore the different types of excitations that we have in these systems, and let us see what those excitations are doing and so on. Okay. So let us say that we are above the transition, so t is greater than 0, and what we do is we are going to think about what does the saddle point approximation actually mean. So the saddle point approximation is saying that you take any field configuration and you are parameterizing by saying that, okay, I am going to find some saddle point which extremizes or minimizes this energy, some local minimum, and I am going to write a fluctuation here about the saddle point. So what this means is that this saddle point renders this S a local minimum, right. So since it is a local minimum, you know that the action corresponding to this fluctuation has to be greater than or equal to 0, because you have already found the field configuration which is a local minimum. So it is very natural to think about these zeta objects as excitations or about some low energy state, right. So you can, so it is natural to think of this fluctuations as excitations about the saddle point, because they increase the energy about the saddle point. Okay. So what are the nature of these excitations when t is greater than 0? Okay. So let us look at them. So if I think about zeta 1, so this is the order, this is the space of the emergent field phi 1 and phi 2, and this point at the origin here, so those are that's the coordinate system in the phi 1 phi 2 space. The point at the origin here is the saddle point value, because the phi equal to 0 or m equal to 0 if you wish, that is the saddle point. So now you see you can have fluctuations about the bottom of this paraboloid like object, right. You can have fluctuations like this. So that the way I am pointing to this is the zeta 1 fluctuation along the one direction. So that is the one direction, and that is the fluctuation. And if you ask what is the energy associated with that, you will see that this is yk square plus t. This we have seen already in the last lecture itself, we have seen this. But how do I interpret this? So think about a harmonic oscillator. So the harmonic oscillator, you think about it as some 1/2 m omega square x square is a displacement here, right. So you see this also looks like zeta 1 square, it looks like the square of zeta, right. So you can interpret this quantity as a frequency square, omega square. You can interpret this quantity as an omega square. So this omega square has two pieces. What are the two pieces? There is this t. Where is this t coming from? This t is coming from the fact that this paraboloid locally, so at a position you are changing the value of the field from the saddle point value, and so you are trying to go, you are trying to change the field phi from the 0, and that costs energy locally, and that energy cost is given by this, you are traveling on the paraboloid here. And what is this k square thing? So even if I am not, even if, so if I increase zeta 1 at a point, it will cost me energy, but it will also cost me energy to be different at different points in space, and depending on what is the wavelength of that fluctuation, I will pay an energy k square. But the bottom line is, you can think of this as if it is looking like some omega square x square kind of term, and therefore you can interpret this quantity as a frequency square, right. So this is what I am stating here. So y k square t is a frequency squared of some harmonic excitation mode, some zeta alpha of k, and it's, so you can think of this like a dispersion, right. Dispersion means momentum as a quantum number k as some label of an excitation, that is what I mean by quantum number, and omega of k, the frequency associated with that, is square root of yk square t. So, I am simply using an analogy to harmonic oscillator, thinking of this as some frequency square, and this is what I call the frequency. Okay. So, this is an interpretation of this. Alright. Now, the question is, there are n such modes here, right? For each alpha equal to 1, alpha equal to 2, you can do oscillations about that, and if you are in n, I can of course only draw n equal to 2. You can think of n equal to anything you want, and there are there are n non-interacting modes. Now, what do I mean by non-interacting modes? That means zeta 1 and zeta 2 don't talk to each other. In elementary language, they are normal modes, right? So, that is what we mean by saying non-interacting modes. And very important result here is that for t greater than 0, these excitations are gapped. What do you mean by that? So, if I let k go to 0 and ask what happens to this frequency, you will see that that frequency as k goes to 0, you can just look at this expression as k goes to 0, it will go to a finite value which is square root t. So, this means that my excitation, my frequency does not go to 0. That means that there is a gap to excitation. So, we say that the excitations for above the saddle point, above the transition temperature or little t greater than 0 are gapped, and the gap value is square root of t. Okay. So, this is what happens when t is greater than 0. So, let us explore what happens when t is less than 0. So, when t is less than 0, we will pick up a non-zero value of the order parameter, and we have already seen this in the last lecture. For example, we have to, the theory will only give you the magnitude of the order parameter, right? We have to pick some direction, or the system picks up direction spontaneously. So, let us pick the one direction. So, in this Procan symmetry phase, this m as a vector has n components, only m1 is non-zero and it is square root of mod t by u, and all the other components starting from 2 to n are 0. Okay. So, now you see, we saw in the last lecture that there is something called the longitudinal mode, right. So, that longitudinal mode has an action which looks like this. We have seen this before. So, let us see what the longitudinal mode is doing. Okay. So, this plane here is the plane of phi 1 and phi 2, and this slightly orangish colored point here, that is the point of m1, right. So, that is where the symmetry is broken. Now, what am I doing? I am actually fluctuating, changing the length of this m1, and I am fluctuating by that by the reddish line that I have drawn there, right. I am fluctuating that way. When I am fluctuating that way, in the energy surface locally, I am actually going up this locally, it is a parabola. So, I am actually creating, I have to pay energy to create this excitation, okay. And therefore, the frequency associated with this, so by the way, this mode is called as the Higgs mode, right. And the frequency associated with this mode, which is called omega Higgs, goes as square root of yk square plus 2 mod t. And this is also a gapped excitation, and the gap when k goes to 0 is square root of 2 times mod t, right. So, this is called as the Higgs mode, and this is, you can think of it as the mode that changes the magnitude of the order parameter. You see, so when I go, m1 is the, so one direction has been picked to be the direction of the order parameter. So, if I fluctuate around that, I am changing the magnitude of the order parameter. So, it is also called the amplitude mode, amplitude of the order parameter, right. Okay. So, for n equal to 1, such modes are called the Higgs mode, right. For n greater than 1, such modes are called Higgs mode. That means that if I have a continuous symmetry, then this mode is called the Higgs mode. For n equal to 1, this is the only mode, so there is no point talking about the Higgs mode. So now you see I have introduced something called Higgs mode, and I am sure that you are aware of all the news articles etc. that you talked about Higgs particle and all that stuff. So you may be wondering, is this related to anything to do with that? So the answer of course is yes. So there is a relationship. So that problem of the so-called God particle etc. has something more required than what we have here. So that requires these kind of degrees of freedom to be coupled to a gauge field etc. But yes, these excitations are very are intimately tied to what happens in the God particle etc. And the name also is borrowed from that literature, and that is why this is called the Higgs mode. Okay, all right. So, but we will not dwell too much in on that point. We will continue. Okay. So, we will call this amplitude mode as Higgs mode only if the symmetry is continuous. If in the Ising case, of course, there is this gap mode, it has the same gap and everything, but we typically do not call it the Higgs mode. Okay. Alright, now we know that there are other class of modes as well, right. What are those? Those are the modes, again our symmetry is broken in the one direction in the order in the ON space, and there are these transverse excitations, right. Remember that we had these excitations transverse like this. So again this orange point is M1, and I am doing fluctuations that are orthogonal to M1, right. So that is coming up, that's showing up in this direction. So this is M1 and I am doing fluctuations like this. So that is my zeta 2, in this case zeta, the only allowed thing is zeta 2 and that is zeta 2, right. So I will be fluctuating here. So if I am fluctuating like this, look at what happens in the energy. I am not changing energy. That means if I want to change the direction of M in a cell, remember I have space and I have the cell, it will cost me no energy, because if I change direction, it is the same, it's the same energy because of underlying symmetry of the problem, because it has ON symmetry. It does not matter what the direction of my field phi is, as long as its magnitude is not changing, my energy will be same. So if I go orthogonal to this, I will not change the magnitude of M, but I will change the direction, but therefore it costs me no energy. So what does it entail? It entails that I will get a dispersion where this just becomes yk square and the frequency is just square root of yk square, right, and these modes are gapless. What does that mean? That means the frequency of these will go to 0 when I take k to 0. Now just imagine what k equal to 0 mode means. K equal to 0 mode means I am going to have a zeta 2 same in every point in space. That is what k equal to 0 means. K equal to 0 means infinite wavelength if you wish. That means that is like a constant shift. Of course, if I take my order parameter and rotate it, turn it a little bit, I will not change energy, because that is the same order parameter, right, in magnitude. So that is what zeta 2 does, it will not change the energy, and that is why I am getting gapless excitations. Okay. So if you think in terms of superconductor, this is like changing the phase of the superconductor. You remember superconductor had a U1 order parameter, which is a complex number. It's like changing the phase of the superconductor, and taking analogy from that, these are also called as phase modes for any n. Okay. So for n greater than 1, remember for n equal to 1, such modes do not exist, right, or for actually any discrete symmetry, such modes do not exist. So for n greater than 1, we have a continuous symmetry, and these modes are called Goldstone modes, and these Goldstone modes are gapless. So the central thing that is coming out of this result is what is called as Goldstone theorem. It says that if you take a theory with local energy density, such as the Ginzburg-Landau theory that we have written down, and you break a continuous symmetry, which is what we have done here, then you are guaranteed to have gapless excitations. And this calculation here is an illustration of this theorem. We can of course give a sort of a formal field theoretic proof of this theorem by coupling this theory to field and rotating the field and so on. So there is a way to do that, but we will not get into such formal considerations. For us, it will suffice to see that if you break a continuous symmetry, you will produce gapless excitations, and we are seeing this by an explicit example like the ON model we have constructed here. You take any reasonable model with any continuous symmetry group and just work out the details, you will be able to see that this is true in and you, of course, you have tried as something with local interactions, etc., which is like writing it in terms of some kind of a Landau energy density kind of thing. Then this Goldstone theorem will work just fine for us. Okay, so you can already see that this Ginzburg Landau theories taught us more than what we thought we had learned. So it teaches us all these nice things. Okay, so very important caveat here is that there is no guarantee that you are going to produce gapless excitations if you break a discrete symmetry, right? So there is no assurance of anything like that. Some accident can happen, I don't know, but there is no basic reason why you should be able to produce gapless modes if you break discrete symmetries. With continuous symmetries, you are guaranteed to have gapless modes below if you break a continuous symmetry. Okay. So we have now explored excitations above the saddle point. Now we will try to get a deeper insight into what these excitations are doing for us and how we can understand some of the results that we found within the SPGA. So density of states of excitations, namely how many excitations are there of a given energy per unit volume of your system. That is what we mean by density of states. This plays very important role in understanding the physics of the system. What do I mean by that? So suppose imagine the saddle point that we have. So there is some energy associated and there are these fluctuations about the saddle point. The question is, how many low energy fluctuations are there above the saddle point, and can I thermodynamically access those low energy fluctuations? And if I can access them and if they are very readily available, then the fluctuations will take over and they will change my physics. So one way to think about this problem is to try and understand the density of states of fluctuations, particularly the ones that are at low energy. So this is what we mean by infrared or long wavelength and low energy excitations. Okay, so we know the frequencies of these fluctuations. So can we find a density of states of this? Okay, so what we are going to do is we are going to use this fact that g of omega d omega will be this quantity here, right? And of course I have to sum over all modes, etc. I am running over k space and I am counting. If I know the dispersion omega versus k, how can I compute the density of states? Now, just using this kind of idea and doing some elementary mathematics, you can show that when t is greater than 0, the density of states will behave like this. G of omega is n by this lambda naught, remember that scale that we had. These are just constants that depend on dimension. Heaviside function is the step function. For positive arguments it is 1 and for negative arguments it is 0. So what it does is when frequency is greater than square root t, so this is what is telling you there is a gap in the system, right? It goes as omega times omega square minus t, the whole square, the whole power d minus 2 by 2. So this is the density of states. We can compute this exactly. Okay. When t is less than 0, you will see that the excitation mode has two branches, right? Oh, so just let me comment here that in this case the n comes from the fact that there are n modes and each mode will contribute to this density of states, so I have to multiply it by n. Okay. So when t is less than 0, you will see that there are two branches. So there is this Higgs mode, which is the amplitude mode, and that will produce this result, same result as before at t greater than 0. There is only one mode, so that is 1, and the gap is square root t, and that is what you have here. Okay. The Goldstone mode will produce something that does not have any t dependence, it is gapless, so it will produce a density of states that looks like this. Okay. So this is the density of states that is contributing to the the thermodynamics of the system, if you wish. So now if you do statistical mechanics with this density of states, you will be able to pull out a variety of results that we have already obtained. Okay. So the question is, what is the nature of density of states near the critical point? So what are the excitations at criticality? So at the critical point, all the excitations, Goldstone modes, Higgs mode from the t less than 0, and all the fluctuation modes for t greater than 0, they all become gapless because t is now set to 0, and you will end up getting G at the critical point goes as this within the Gaussian fluctuation approximation, saddle point plus Gaussian approximation. So you will end up getting this density of states. And this friends is the clue to our understanding of what is happening in the Ginzburg-Landau theory. So you will see that this goes as omega to the power d minus 1. So now you see, if you plot this quantity as a function of omega, you see that when I am in, let us say, d equal to 1, then there is a finite large number of states at 0 energy itself, right. That is very close to 0 energy, there are lots of states. When I come to d equal to 2, this goes linearly, so there are states at low energy, and when I come to d equal to 3, there are somewhat less. When I start going to d equal to 4 and 5, this becomes even smaller. So what understanding you can gain is that the density of states of low energy excitations, they start to fall as you increase spatial dimension, which means that the effect of fluctuations become lesser and lesser and lesser as we go to higher and higher dimensions. So based on this, we can see that dimensions less than 4 have significant density of states in the infrared, and those fluctuations will thermally be activated because they are low in energy, and they will ruin the nice things that we found with the Landau theory, and the fluctuations may become large, because they are strong and so on, and then we have stopped at the Gaussian order, maybe the next orders are important. So all those effects will start to come and become very important when you are in dimensions less than or equal to 4. But above that, you will see that these fellows are essentially 0, and that will help us mitigate any effects of fluctuations, and Landau theory probably there may be some qualitative changes, there may be some quantitative changes to the jump in the specific heat, etc. But other than that, Landau theory will work just fine. So this gives us an idea of why Landau theory is working well in d greater than or equal to 4, and it does poorly, and the answer lies in this density of states of excitations. So you can hopefully appreciate now that Landau theory didn't help us connect with didn't help us reveal the critical exponents, etc. of different systems with different symmetries and different dimensions, but it does offer us an insight into what is happening at the critical point, and you can see that it's showing us that the critical point has gapless excitations. It's showing a variety of these very nice physical insights. Okay, so it's a good time to summarize the lecture now. So what we did in this lecture was we took a deeper dive into the Landau-Ginzburg theory within the saddle point Gaussian approximation. We looked at a theory with 3 coupling constants based on some very nice physics based arguments. We were able to argue that there are these 2 length scales. We were able to interpret what those length scales are, and we were able to show that to see fluctuation effects, you have to be within a regime of the critical point, and in some dimensional distance to transition, it is determined by the parameters of the theory y and u, and they are given in terms of this length scale. So, we found out what is this thing called as the Ginzburg criterion. So, this if you are not within this distance to the critical point, you will not see any significant fluctuation effects. Okay. This allowed us to understand, rationalize why there is a difference between superconductors and superfluids, both of which are undergoing an O2 symmetry breaking or a U1 symmetry breaking transition. Okay. We explored the excitations of above the saddle point, and we found that for t equal to t greater than 0 on the positive side of the transition, on the symmetric side of the transition, there are n gapped modes with a gap that scales as square root t, and they become gapless when you go towards the critical point. And for t less than 0, there is one gapped amplitude mode which we call the Higgs mode, and n minus 1 gapless Goldstone modes. And most importantly, we saw an illustration of the Goldstone theorem, which says that if you break a continuous symmetry and under very reasonable conditions of saying that your free energy or the action is an integral of a local density, you will see that the system will have gapless excitations. That is guaranteed, right? Okay. And then we went on to explore a very physically appealing idea of density of states of these excitations above the saddle point, and we were able to uncover this very nice result that there is a significant low set of low energy excitation accessible to the system in d equal to 1, 2 and 3, and they become increasingly smaller and smaller, and they sort of become non-existent in higher dimensions. And it is this absence of low energy excitations in higher dimensions that is sort of protecting the Landau theory from the Landau exponents from fluctuation effects, etc., and that is why the Landau exponents become better and better when you go to higher dimensions. So, this is very insightful, as you will readily agree. Alright. So, what is it that we have to do next? So, I am going to claim that we have to dive deeper into the Landau-Ginzburg theory. So, we will discover more things there. In particular, we have to study what are the correlations, like for example, how correlated are the fluctuations of the fields and so on. So, let me pose this question in a different way. So, you see, we said that the Goldstone modes do not enter the thermodynamics. So, then why are we even talking about them? Should we be worried about them? So, I am sure that you will find this question very intriguing, and I am sure you will be looking forward to the answer which will come up in the next lecture. So, see you then. Thank you.